Hello students, in the last year you have studied the S and P block elements. In this semester you are going to study D and F block elements. Today we will discuss D block elements. What are D block elements? Yes, elements which involves the filling of d orbitals in the penultimate shell are called as a D block elements. In the periodic table, these D block elements are placed in between S and P block elements, and their properties are changes from electropositive S block to electronegative P block elements. That's why they are also called as transition elements. The D block elements of the periodic table that consist of a 4 series called first, second, third and fourth transition series. Let us discuss the first transition series. The elements from scandium to zinc that constitute a first transition series. Let's see the electronic configuration of that. The general electronic configuration of a D block element is n-1 D 1 to 10 n s 1 to 2. The first element is scandium. The atomic number of a scandium is 21 and the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2, or we can write it as AR 3d1 4s2. Look at the slide here. These are all the electronic configuration of the other elements of first transition series. If we observe it carefully, the electronic configuration of a chromium and copper is different from others. Why is it so? Here the expected electronic configuration is 3d4 4s2 3d9. Expected electronic configuration is 3d4 4s2 and 3d9 4s2, but the configuration is 3d5 4s1 and 3d10 4s1. This unexpected electronic configuration of chromium and copper that can be explained on the basis of extra stability gained by the half-filled and completely filled orbitals. That extra stability that can be explained on the basis of two factors. One is exchange energy, one more is the pairing energy. What is exchange energy? Here the electron in the various orbitals of the same subshell or in the different subshell can exchange their respective positions. During this exchange process, the some amount of energy is released. That energy is called as exchange energy. As the number of exchange increases, the exchange energy is also increases. Now we consider the D5 configuration. Here there are 5 electrons in the orbital. So if we consider the first electron here, then that electron can exchange with the other 4 electrons. If we consider the second one, again that can be exchanged with the other 3, and third one exchanged with the 2, and fourth one exchanged with the 4. So the total number of exchanges are 10. But in the 3D4 configuration, only 4 electrons are there, and if we consider the first one, that can be exchanged with the 3 electrons, second one with 2, third one with 1. So the total number becomes equal to 6. So as the number of electron increases, the exchange energy is also increases. So exchange energy increases means the amount of energy released increases, so the element which acquires a lower energy. Always lower energy orbitals or the elements are more stable. And the electronic configuration of a copper that can be explained by considering the pairing energy. Pairing energy is also similar to that of the exchange energy. Pairing energy means it is the energy required for the pairing process. So as the pair the electrons, as the paired electron increases, pairing energy is also increases. Here also the elements gets a lesser energy. So in order to acquire a extra stability, one of the 4s electron is shifted towards the 3d orbital. And let us discuss some of the general properties of the d block elements. First property is atomic radii. Atomic radii means it is the distance between the center of the two nuclei. The atomic radii, that is, decreases with the increases of atomic number, or it is decreases along the period. As the nuclear charge increases, the atomic radii decreases. How does the atomic radii decreases with the increases of a nuclear charge? This can be understood by calculating the effective nuclear charge by using the formula Z effective is equal to Z minus S, where Z is the atomic number, S is the non-valence electron. Now we consider the example that a scandium, the atomic number is 21, so Z is 21, and yes, that is the non-valence electron, here it is 18. The non-valence electron means the electron present in the innermost orbital. Here 3d1, 4s2, these are the valence electrons, these are the valence electrons, and from 1s2 to 3p6 are the non-valence electrons. So Z effective becomes equal to 3 here. Now consider the next element, that is Di. The atomic number is 22 and the non-valence electron remains the same because the one electron that is added to the 3d orbital. Here the Z effect becomes Z effective nuclear charge. Here the effective nuclear charge becomes equal to 4. Atomic number, with the increases of atomic number, effective nuclear charge is also increases. Nuclear charge means it is one of the positive character of the nucleus. So as the positive nature increases, it pulls the electrons. So contraction takes place and the atomic radii decreases. So because of the contraction, atomic radii decreases. The next property, that is a ionic radii. It is similar to that of the atomic radii. Ionic radii is also decreases along the period. That means it is decreases with the increases of a atomic number. The next property, metallic character. All the transition elements are metallic in nature. This is because of the presence of less number of electrons in the outermost orbital that can be easily lost. The next one, the molar volume and densities. The molar volume, that as decreases with the increases of atomic number, so that the density increases. Next one, melting and boiling points. They generally exhibit high melting and boiling points. The next property, that is the oxidation state. See here, some of the oxidation states of a first transition series were given here. The scandium, that exhibit +2 and +3 oxidation state. It exhibit +2 oxidation state when it uses 2 of its 4s electrons. It exhibit +3 when it uses 2 4s electrons. It exhibit +3 oxidation state when it uses 2 4s electrons and 1 3d electrons. And from this we can define minimum oxidation state and the maximum oxidation state. The minimum oxidation state means it is the number of electron present in the 4s orbital, and the maximum oxidation state for scandium to manganese, it is the number of electron present in the 4s orbital and the 3d orbital. But from Fe to Zn. The minimum oxidation state remains the same, that as the number of electrons present in the 4s orbital, but the maximum oxidation state will found to be differ. That is, here for ion the total number of electrons are 8, but the maximum oxidation state is +6. Thank you.